let's talk about something interesting. Okay, never mind. A few words about me. So this is my avatar, and raise your hand if you have seen this presentation before. Okay, great. So fans are here. I love you guys. So my experience in IT maybe split it into two parts. So the red part is system programming. It's C, C++, Julia is different devices like cards and chipped cards and etc. And antiviruses. So it's a different device and low-level system programming. And the second part is web UI. And right now I'm a developer at SoftServe, a web UI developer. So, but we will talk a little bit about different topic today. So we will, I will tell you about evolutionary principles, about artificial intelligence, genetic algorithms, and I will tell you about my experiment. This is JEVO. This is open source application on GitHub, and I will show you the results. Okay, so first of all, about the goals. So I have many goals. First of all, it's personal interest. So I'm personally want to create a simple version of artificial intelligence. This is like a main goal. So the second item is community. Community around this question, around genetic algorithm and evolutionary programming. And I want to increase my team because we have only 2 developers right now. And yes, the artificial creation. So if we're talking about assumptions, so before we start, we have to conclude that we may create artificial intelligence through the code. So maybe it's possible that we may create some program which behaves like an artificial intelligence. And the second one is this is an incremental process. So this is a step-by-step process. On each level, we have a little bit more complicated artificial intelligence. So we have different levels, something like that. And okay, who knows this guy? Okay, 1, 2, okay. This is a Charles Darwin, and I think you know Charles Darwin. So let's talk about definitions. So if you're talking about organisms, everything I'm talking about, you may create the parallels between the computer models and the nature. So for example, organism it's me, for example. It's insects, it's cows, it's beavers, and so on. So if you're talking about computers, the organism is a computer program. Okay? So the next one is mutations. Mutations, it's changing of DNA in nature, and regarding the computer programs, is a changing of the code. Okay, simple. So selection. Selection is a process which kills the less adaptive organisms and just don't kill most adaptive. Heredity. Heredity is an ability to pass all your properties to your child. So for example, if we're talking about computer program, we may copy this program, make some mutations, but most of the properties of the program will be the same. Okay, these 3 items, this is the basis for evolution in the nature. So we'll take this basis for our computer models. I will show you the video. So the gene is like a basic structure in a DNA, and if you change the gene, you will change some properties. So for example, it's color of eyes, shape of your body, and so on and so on. So crossover, it's just mixing the DNA material. So in case of computer programs, you take one program, you take second program, mix them somehow, and create another program. And this is a like child program, something like that. And before last, fitness function. This is a mechanism which may somehow get the level of adaptiveness. So for example, you give the organism to this function, and it returns some number. So, for example, for first organism we have number 1, and for second number 10. It means that second organism is more adaptive, and we have to kill the first one. And the last one is population. It's just many organisms in a field, some area. Okay, some few words about genetic algorithm. What is genetic algorithm? Genetic algorithm is a search algorithm. So if you take some problem and you know that there are many solutions for this problem. So this algorithm just try to check different solutions, and it measure what solution is better, what solution is not so good, and so on. So, for example, you can see this is a picture of Darwin from the left. This is an original, some JPEG file. And from the right, you can see the intermediate, like middle results of working of such program, which just draws a circle, draw it in some position, use some color, some grayscale color, and use some radius. And fitness function tells the program, okay, this picture with this particular circle is a little bit better for us. It's a little bit more similar to original picture. So this is how it works. Okay, if you're talking about computer code, so we may program or create some program which implements the genetic algorithm. So it's very simple. So first of all, if you're talking about organisms, we are talking about solutions. So you may think, if I tell you an organism, you may think, okay, this is a solution. So first of all, we create a big amount of solutions for some abstract problem. After that, we evaluate every organism, every solution. So we may, using the fitness function, we may take this solution and mark some numbers. For example, 1 takes this organism and mark another number, and so on. So after that, we go to the loop. And a loop is the custom. So for example, we may reach the time or reach the resources or find the solution, any case. So inside the loop, we just take 2 parents or maybe more, mix the genetic material, mutate them somehow, produce the children, and give these children put into the new population and just kill the less adaptive organism. So this is it. This is very simple. And this is a simple video regarding how the genetic algorithm works. So let's imagine we have to create the motorcycle. So program know nothing about motorcycles, about dynamic, about different physical, about environment, and so on. So this is a 2D, two-dimensional space, and it will be a road, something like this, and we may create motorbikes through different shapes. So for example, we have circles, we have triangles, and we have 2 types of circles. First one is spinning around, and the second one just not. This is it. And we may combine these different shapes between them. So let's take a look to this algorithm. Okay, this is the first population, just random creation of some motorbikes. So the second population will be created from the best one. This is the best one. As you can see, it consists of 3 wheels. And the first one is not spinning. So only left one is spinning, okay? It's a little bit more. So the distance from the beginning, this is a measurement for fitness function. So this is Zen, by the way. So this is first, 6, yeah, it's a little bit problem here. Okay, yes, this is the best one. So as you can see, okay, this is just intermediate like results. So without like all the calculations. So as you can see, we have, does it work? Yeah, we have 2 wheels, and the left one and the right one are spinning, and we have something like a joint here. So it's similar. So if all this construction will turn it around, it will work in any case. So the second interesting video, it's regarding Carl Sims' works. in 1996. So he used the supercomputer at that time to create the virtual creatures, and he took the different parallelepipeds and combined them using the simple muscles. So one muscle may just stretch and return to the same state. And this is it, all the rules. And the like goal for the system was like moving from point A to point B, moving under the water, moving on the circle, and so on. So let's take a look on this.
This demonstration shows virtual creatures that were evolved to perform specific tasks in simulated physical environments.
So
Swimming
this is
speed was
underwater
used to
moving.
determine survival. Most of the creatures are results from independent evolutions. Some developed strategies similar to those in real life.
Yes, it's very similar to
Once
the
they're
snake, by the
evolved,
way.
multiple copies of these creatures can be made and simulated together in the same environment. The next group of creatures were evolved for their ability to move on a simulated land environment with gravity and friction. Some simple solutions with just two parts.
This is moving by circle.
Some seem like they could use some assistance, while others were fairly efficient, such as this
is moving
rowing-like
from
behavior.
point A to point B, and the speed is very
Here
important.
is an odd cousin of the previous. A mutation caused him to tumble. Some creatures evolved to incorporate contact sensors in their control systems.
The same on circle, yeah.
Here is another inchworm-like creature that tends to go in circles. This was actually a creature first evolved for its ability to swim in water, then later put on land and evolved further. A successful sidewinding ability resulted. Here is one with a hopping style. The protrusions on its arms seemed to help prevent it from tipping over. This was the fastest, with a successful galloping-like stride.
Yes, this is a galloping style. This
group
very
was
interesting.
evolved for
This is
their
a jumping
jumping
ability.
ability. This group was evolved for their ability to adaptively follow a red light source.
Yeah, this is under the water,
The resulting
and you
creatures are
have
now
to
being
follow
interacted
the
with.
red dot.
A user is moving the light source around as the creature
This
behaves.
is something
This one seems to flail randomly,
ununderstandable.
but somehow still manages to approach the light. Perhaps
it works.
it
It
was mean
works,
to
as you
move the
can
goal
see.
away just as it arrives. Here is one that has propeller-like fins which are
This is
tilted
an
depending on the
interesting
direction
one
of the
because
light.
this is a
It can
propeller-like
adaptively swim up or
mechanism
down
which
very
we
well.
produced by evolutionary algorithm.
This final group of creatures was evolved for their ability to
This is
compete
a
for control
competition,
of a green cube.
and you have to reach.
The creature closest to the cube at the end of the simulation is the winner.
If you near the cube, you are the winner.
Here, a strategy first arose for simply tumbling towards the cube.
Okay.
Then one learned to block out his opponent. But then later one learned to overcome the obstacle by climbing over it.
Yeah, he is good.
Some pinned down their opponents. Some covered the cube with protective arms. Others simply unfolded onto the cube.
Okay, I think you
The
got
success
the
of a
idea.
strategy is often highly dependent on the opponent.
Okay, because the video is really long. So, if you're talking about real products, we have different types of real products. So on the left, you can see. By the way, you may type. You may go to the Wikipedia and type genetical algorithm, and you will see this picture. This is an antenna, and NASA in 2006 created this antenna using the genetic algorithm. And the problem was that in space you have the high radiation level, and it doesn't work in the same way like on Earth. This is why they produced this antenna through the genetic algorithm. They used different materials, they used this strange shape, and so on. And this is a real product which is in space, and it works. The second example on the right, this is a lens system. So if you have the lens system, for example, you have a camera, yeah? It's a simple camera, and you have to have some great image, like an output, like cheap material, the distance between these lenses, the curvature, and so on. So there are many possibilities to create such a system. So the special application was created which used the genetic algorithm, and it produces this special example. It produces the such lens system which works better than we have, than people created, so engineers created. A few words about my experience at home. So I created an artificial application which okay, this is artificial life software, and it creates the digital organisms. This is like computer programs which lives, eat each other, compete, hunting, and so on. So, and as a result, we may produce different types, different complexity of artificial intelligence. So, regarding its parts, so we have a piece of memory. So this is like, okay, it can consist of height and width, and there are different dots on this memory. So we have three types. First one is just empty dot. The second one is like energy. So organism may eat the energy. And the last one is organism. So this is an example of the code of one of the organism. And we have virtual processor which run all the code from all the organisms. We may mutate this system. We may clone and produce the children. We may there have an energy inside, and this is how we measure the quality, the adaptiveness of the organism. So if you have more energy, you are the best. And position, this is just x and y coordinates in this system, and memory, internal memory for some internal usage. So they may read the memory and push some data into the memory. And regarding the code, it consists of variables, functions, conditions, it's if operator, loops, it's for operator, it's some mass operators like plus, minus, and etc. Look, so they may look into some point with some special coordinates, and they may step up, down, left and right, and the same with eating. So they may eat something up, right, left, and down. So this is it, and all this stuff inside one manager. One manager is a system process. So system process, this is a real process in the operation system, and you may create a connection through the terminal, type some command. We have a remote API for this, and take some results. So for example, how many organisms is there, take some code, specific code, and etc. So we also have a visualizer. Visualizer, it's this is like real-time video, and we may observe what is going on there. And we also have a statistics module which collects all the statistics through the time, and I have a really big amount of statistics. It's about 1 gigabyte of JSON right now. So my future plan is create the cluster. So this cluster will manage different managers, and this is like a big map in computer games. So if you have a big cluster, you have many organisms, you have big map, and it will be faster. And a few words about Julia. Julia is a computer language which was used for this problem. Raise your hand if you know this language. Okay. One guy. Great. So it's new, by the way. It's the result of 3 guys from MIT in 2012, as I remember. And okay, it consists of important parts for this problem. So, for example, it has green threads. It's something like coroutines in Python, and you may create a really big amount of threads in a system. And networking part is also useful for this problem. Metaprogramming is an ability to change the code through the time. So, for example, you don't need to stop your program, and you may change your code while your system is working. So performance, it's very important because this language is very fast. It's the same level like C language. So for example, it's faster than JavaScript, Java, Go, and different languages like Python and so on. So LLVM is an ability to run these applications on different operation systems like Windows. I tried Windows, Ubuntu, and macOS right now. Okay, this is a screenshot of a real system. And as you can see, okay, does it work? Yeah, so this is a visualizer, and you can see this green dot. It's an energy, and these organisms may eat this energy. This is a terminal. So all these terminals just connected to this server. So it's just a log. Something was disconnected, the backup was created, and so on. So, and you as an operator may type some command here. So for example, we type a term get amount and the amount of organisms in this system 457. And this is a like best organism in the system, and this is a quote of this organism. Okay, the video, the interesting part. So okay, okay, nothing. Okay, it will be a little bit increased. Don't be afraid. So as you can see here, here, and here, there are some movements. And okay, okay, this is a group of organisms. They are ancestors, and you can see this black area. This is like eated area. And they started to move, they started to compete. So for example, this is an example of eating. So as you can see, this is a green block, this is an energy, and voila, he eaten the block. And this is another example, the same, just eat and go away. Okay, and the next one, the same picture. Okay, walking around. Yum yum. Okay, so it's a very important idea here that I didn't tell them how to move, how to eat, what to do, and what is going on here. So the second video is more interested, and this is an example of collaborating. So they started to collaborate and created small groups and eat together. So let's see. So this is a little bit in increased speed, so don't be afraid again. So as you can see, this is a small group of creatures, and they just eat everything on the way. And the second part will be a little bit increased. Okay, so this is one group of organisms, and the interesting algorithm is here. So it was created by them. They write their code in this way. So the first organisms don't eat each energy, and they just pass the energy to the last organisms. So the second group, oh my God, is here. It's not so productive, but it's also eats some energy on the way. So, okay, this is the result. Okay, maybe one question. Raise your hand if you know what Luca is. Okay, Luca is a last unified common ancestor. The same term in the nature, so we have such ancestor in the nature. So this is like a first replicant. So the same on this system. This is a start program, so it's just empty. So after 3,000 of generations, 3 important mutations was added. So first of all, this is a var25 variable was added, and step left and eat left. So this code was produced by the system, and this is a very cool algorithm for such system. If you, for example, the first example just empty. It does nothing. But the second one, this is, by the way, the ancestor of the first one, it may move to the left and eat from the left. The next step was, this is like 3000 generation plus. The next step was by adding, you can see the eating function is calling twice, and they started to use plus operator, and this is how they eat more. And the next algorithm is a little bit more complicated. So as you can see, the movement starts to be to the right. And this is how they understood that if you eat just up and left and right and down, this is a more, this is a greater algorithm for living. And the next step was, by the way, as you can see, this variable here and variable here, it means that this is an ancestor of this one. So it's very important because in nature we have all this ancestor through the time. And the next step was creating the diagonal moving. So as you can see here is left step and down step. So this is something like this. And the next part, it's eating part, is the same, a little bit greater results because we use multiplying operator here. The next step is more complicated. Don't try to understand this code, by the way, because it's impossible. Okay, this is an interesting example because this is a track of this organism. So the green part is the beginning and the red part is like end point. So as you can see, the movement of this organism is a little bit complicated. And if you loop this moving, and you will have something like this, chick, 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 and so on. So this is how they eat more. And the next one, this is the first place where function is used. So for example, there's a function, there's a function call, and I will tell why function use is very interesting. So, and another interesting part is error here. So for example, var66 is not defined somewhere here. This is because an annotation was produced which removed this definition at the beginning. So, but it's not a problem because the main program is working fine, and you have exception only on this line. So this is how errors are. For example, we have the same problems in our DNA. So in a computer code, the same problems. Okay, this is the next step. This is the last slide with the code because I have a like bigger result, but I can fit them into the one slide. So, okay, don't try to understand this again. This is a moving. As you can see, it's almost the half of the code, and the next one is eating. The same, like the half of the code. So moving and eating is very important function for this these organisms. And the next interesting thing is calling of the function. It's important because the size, the entire size of the code is critical, because if you have a big code, you have to eat more because the system grabs your energy faster. So, okay, this is an example of, so as you can see, we have like root code here. This is the one function, this is another function. And this is an example how this particular organism move itself. So this is one function, trajectory of moving, this is another one, and this is the result. So if we combine all of this, you can see that this is the beginning, green one, and red one, this is like a final destination. So he moves something like that, after that here, and if you loop this system, you will obtain the moving by diagonal. So it's very like a cool algorithm at that time, because in this case you may eat more. So let's assume, so we started from simple moving to the left, continue with moving to the right with two positions, and the next is diagonal, the next is some complicated moving with some special trajectory, and the next one is very complicated moving. So, and so on. So after that, the system produced like more complicated trajectories, and the system used if operator cycles and more. So this is a charts. This is a real data from 1 week of work in this application. So as you can see, the green one is moving and the red one is eating. So as you can see, it's important. Okay, this population age, it means that this is something like a time. So here is a last judgment. All organisms died at that time. So, but it's important that the trend goes up. It means that the amount of eating and amount of moving were increased through the time. So the next graph, the next chart is using their, this is a amount of functions, yeah. So, I'm sorry. This is the amount of functions, and this is the amount of function calls. So as you can see, the same, the trend is great. We have like goes up, and it means that in general, this population complexity is increased through the time. And the same for different other aspects, like for operator using, condition operator using the same picture, the same for memory usage and simple vision usage. The problems. Okay, we have different problems here. First of all, if we're talking about artificial intelligence creation, the performance is very crucial. So yeah, I tried this on my home computer, and it's impossible. It's impossible to reach some real results. So this is why we need the cloud for this. And the network speed is another problem because we have limitations, some hardware limitation, and we may only optimize our code. This is why I use a special protocol based on TCP to solve this problem somehow. The next is visualizer speed. Okay, this is not a real problem, but I tried to use Canvas. It's impossible because it's very slow. And right now I'm using the OpenGL Canvas for this. The compilation speed is also crucial because we have to recompilate our code every time during system is working. And the last one, the bigger problem here is that if we're talking about artificial intelligence, it's a very, very slow process. Okay, we have some problems with the language. It's very young, and we don't have debugger right now. It's a problem, by the way. But as I know, in version 0.6, they will show us a real debugger from the developers, the core developers. And amount of libraries is not so big. I think it's a medium, but for this problem, this language is like best choice. Okay, future plans. First of all, it's a distributed system. It will be a cloud which will calculate all the organisms, all the code, and produce some real complicated behaviors. I need to implement the crossover. So right now it's just simple cloning the code, adding some mutations in it, and that's it. The next one is code complexity. So I use just few code parts. It's variables, it's functions, it's cycles, and etc. So complex word is also very important. I need to have something like weather, holes, water maybe, and day and night, and so on. So social behavior is an ability to speak. So if you're an organism, it's very important to speak with your neighbors, and hunting, for example, is also very important. So world interaction is, okay, this is I think it's a complex word. So this is an ability to interact with the surface, with this water, with the weather, and etc. So if you are interested in this project, you may make the photo of this slide, and this is how you may add, you may write me. I have a YouTube channel, I have a Twitter and Facebook group for this project, and it's open source. It's on GitHub. You may see the code, do some experiments at home, and so on. Okay. Okay, questions, guys?
Questions about artificial life. Where is volunteers with microphone? Without microphone, right? Is it? Well, I see the question. Where is the volunteer with microphone?
You are the volunteer.
Okay, could you please raise your hand? Thank you.
Hi, my name is Igor. A very interesting presentation. I really appreciate that your endeavor to actually to take their genetic algorithms from their simple data, like data mining stuff, to their more like a coding and trying to develop a new software set. But how do you actually, if you see that problem anyway, but how do you actually going to address the following challenge? If you try to replicate the human behavior or like any life behavior, it's known that our bodies and our DNA has been built of their how do you call this small proteins.
Yeah.
And even the simple protein, molecule protein, is actually been built from their 10 atoms.
Yeah.
That behaves absolutely, in a various order.
Yeah.
So your software that you're trying to create is essentially built on the binary logic, right?
Yeah.
And then the amount of variance you experience with the performance even right now, and the amount of variance if you'll try to replicate it like in the real life, like totally replicating the human behavior is immense. So eventually, you might actually come up with the idea that it's not capable with all of the compute power that is currently available for human beings.
Yeah, you're correct. So we don't have such like resources right now. And yes, it's impossible to obtain the result like we have. I mean, our brain, but we have on the current level of computer power, we may talk about some low-level results. So, for example, my plans to create something like insects, for example, or something like mouse or rat, maybe not more. I don't think it's possible to reach some type of the form of the monkey, for example. It's impossible, I think. Yes, I understand the problem because I will check this in cloud, and I will share the results. I don't think it will be something really cool and really complicated like we are, but it's still interesting because if the Moore's law is working, it's possible in the future to have like better results for this problem. So yes, I understand the problem. I understand that I can produce such things like our brain, yes. But intermediate result is also interesting, so that's why I try. So this is a research.
Next question. Next question.
Hey, can you talk a bit more about your implementation of mutation for Geo case? Because you can kind of see how you will implement mutation for like the initial bike example you had in the beginning of presentation, but it's like not very trivial to combine code, right? You cannot just take pieces of logic and stick them together. Like they might be like meaningless.
Okay.
Yeah.
So okay, so I have pieces like genes. I have genes. So genes is variables, functions, loops, condition operator, and so on. So this is like finite list of things. So, and I have a tree. I'm working with AST, abstract syntax tree. So this is like intermediate, this is like bytecode in Java, for example. This is a tree, real tree, and I can navigate through the nodes. And randomly, I choose one node and choose the type of the mutation, adding, removing, changing. So I have some functions with probability. Okay, so I choose one. So for example, adding. After that, I choose the gene. So for example, it will be the if operator. And I insert the if operator here. I check, for example, I take two variables on the left and on the right, check if I have, so I have additional meta information for this tree in the memory. And yes, and the produced code should be compilable. It shouldn't contain some errors inside, syntax error, I mean. It's possible to have different exceptions in the code. It's okay. So as you can see, we have these exceptions, and I have the database of exceptions. It's also interesting question. So this is how it works. So after that, I have this abstract syntax tree, and I pass this tree into the compiler, and compiler compiles the machine code, and I run this machine code. This is it. In real time, it works in this way. So next question.
Here.
We may discuss it after the presentation, so it's not.